Well, thanks, Juliana, for having me. I'm Sahil. I run Space, a 3D modeling company. We turn photos into models. And what I wanted to introduce today is the Big Circus Model, which is a model of cosmology based on three core ideas, which is no galactic recession, photon hubbling, and eternity, the concept of eternity. And the recent weeks have been something entirely unexpected. And how I got here was, well, originally from a lifelong curiosity in cosmology, which started picking up last year with a lot of work done by Wolfram on his hypergraph model of the universe. And he came to an interesting conclusion, which is that in the process of trying to find the rules of the universe, ultimately you have to come to the conclusion that all possible rules can run. And I wanted to take that a step further, that the rules eventually have to turn into themselves. So that's one thing that I was thinking about. Meanwhile, I was looking at the SI unit system, the meter, the kilogram, the second, just very basic concepts of length, mass, and time, and how they were defined. And they were originally defined by everyday objects like a volume of water or a distance across the Earth, and then or the rotation of the Earth, and then how they were redefined into fractions of the speed of light and Planck's constant. And then I started looking into Planck's constant, and I came across a coincidence that Planck's constant equals the mass of the proton times the radius of the proton times the speed of light times pi/2, precisely. And that wowed me, that this is so precise and so close, and that Planck's constant could be represented in terms of things more fundamental. So it's not a fact, it's a coincidence, but it's a very precise one, and it involves quantities that are more fundamental and experimentally measured, which gives me reason to just consider it for a bit. So while I had that thought in mind, I thought about plugging it into Dirac's large numbers hypothesis, which is this famous 100-year-old equation, or approximate equation, that the radius of the universe over the radius of an electron is something like 10 to the 40th, and that the radius of some charge extreme over the radius of some gravity extreme also equals 10 to the 40th. But that was always an approximate equation. It wasn't, he didn't have the measurements of Hubble's constant. He didn't have measurements as precise as we do. And it was just left as that. So I thought about considering it with our latest measurements, and I came across a relationship between all the fundamental constants in a way that was symmetrical, extreme, and precise, and all-encompassing, as in there wasn't one fundamental constant that was left out. And what it was the Hubble radius over the radius of an electron mass photon equals the proton's charge radius over a proton mass black hole radius.
Is that it? I'm sharing my screen.
This is it. I first wrote it by hand and then thought I'd put it up in some italicized script so that it can be memed. And the left-hand side is a ratio of the longest, cosmically interesting length, over the shortest cosmically interesting length, I think, or particularly interesting length, which is if you take it's the radius, the wavelength of a gamma ray photon from annihilating an electron, and then that over 2 pi, and that radius. And then the right-hand side is the radius of the proton charge as experimentally measured. And that measurement only came out in the last 5 years or so to high confidence, which is probably why it's taken some time for this to come out. And then the denominator is the Schwarzschild radius of a proton mass. So this is something that I think gives some credibility to the notion that the proton really is a fundamental kind of scale of mass and charge, and that the Hubble radius is derivable from atomic properties. Or in other words, that the universe is a macrocosm of the atom. So
can I
sure.
ask you a question? Sure. Can you go over again the equation? So the top left part of the equation it's something representing the photon, and the bottom left. Can you go over again?
Yeah. So the top left is the Hubble radius, also known as 13.8 billion light years.
Which is well known as the age of the universe, usually, right? Is that right? Or 13.8 billion?
Yeah, I came into this thinking it was the age of the universe. It's called the age of the universe. But I'll fast forward a bit, and I came away from this thing realizing that 13.8 billion years is a constant and not an age.
Yeah. And then the bottom left is what?
The bottom left is the Compton radius of the electron.
And what does that mean?
That if you have an electron and it gets annihilated from a collision with the positron, and it turns into a photon, and that photon has a wavelength, that wavelength over 2 pi is this quantity.
Mm-hmm. And cool. And then the top right and the top left. Top right and bottom right.
Top right is the charge radius of the proton, tentatively. And that's from experimental measurements and the previous coincidence involving Planck's constant. And the bottom right is, if you take the mass of a proton and compress it so it becomes a black hole, that's its radius.
Mm-hmm. Cool. And so what would that equation mean? Like what? Yeah, can you go a little bit in detail, like why that's important that they are like equivalent, the two ratios?
Yeah. What amazed me is that a cosmically large quantity is derivable from something so small. You know, the smallest stable, abundant thing, the proton. Mm-hmm. Well, the electron's stable and abundant, but the proton is, the center of the hydrogen atom. And that gave me reason to look more into Hubble's constant, big H, which is 1 over 13.8 billion years. And then I thought, I've always been told that it's an age. It's the age of the universe. But then I thought, how can it be an age if ages go up? Ages, they go up, right? And then, but it's such a beautiful equation that can I just consider that it's a constant? So I did, and then looked at the actual measurement that resulted in what we know as Hubble's constant, and tried to understand the history. So what I found was that what Hubble's constant, all it is a measure of the rate of redshift, which is the rate at which photons lose energy while traveling. So that's all that Hubble measured 100 years ago in his lab in Mount Wilson Observatory.
So that's your theory, right? Like your theory is that the Hubble constant, which is 1 over 13.8 billion, is the measurement of photons losing energy. Is that right?
Right.
And another question: do protons lose energy as well, traveling through? Like, how does the photon lose energy? Does it get interfered by electromagnetic waves, or does it just lose energy? Maybe you don't know the answer. Maybe the answer is that, okay, it loses energy, and that's what your assumption is right now.
I don't know if the proton loses energy while moving. It's an interesting question. The photon losing energy, my guess is that it's just the cost of traveling. That if you imagine the photon moving through the universe, it's in a sense it's forging a path, and it costs, it takes work to move, and it was originally called photon fatigue by Fritz Zwicky about 100 years ago. It was later poorly branded as tired light.
Yep.
And I think it's time for a new name, photon hubbling. The photon gets hubbled as it moves. And then to test this idea, I tried to find all the available redshift data. And actually before that, I want to mention that Hubble himself, when he took those measurements, he left it open as to the cause of it. He didn't make any claim. But the scientific establishment shoehorned this interpretation that it's the Doppler effect, that apparently all galaxies are flying away, which results in very odd conclusions that apparently some galaxies are moving away at 90% the speed of light. And that's just the beginning of some of these crazy consequences.
Yeah. So for our viewers, can you explain a little bit what's the Doppler effect and some of the consequences of, the Big Bang theory that don't match what we're measuring? So some of them are galaxies that are older than the age of the universe, some galaxies that were formed a billion years after the Big Bang had some heavy metals and things like that. So first, going to the Doppler effect and what the Big Bang theory assumes.
The Doppler effect is the change in a wave when the sender is moving. So in the simple case, like the case of a fire truck, if a fire truck is moving towards you and has the same siren that it's blaring, that the pitch of that siren will be higher because the waves look like they're compressed as the truck's moving towards you, and vice versa. If it's moving away, then the pitch goes down. And similarly, in the case of light, if a galaxy is moving towards you, the intensity of the light goes up, or I'll just say the frequency of the light goes up, and then if it's moving away from you, the frequency goes down. And so what the scientific establishment did was attribute the cosmological redshift to the Doppler effect, which was their big mistake. What they should have done is said, we don't know. And, let's just think about it.
Just going a little bit, because this subject is a little bit complex. So you can correct me if I'm wrong. So what some scientists assume was that they could see there's a redshift, from galaxies that are far away from, the Milky Way. And what they assume is that the universe is expanding at an accelerating rate. That's why you see red waves instead of blue waves. Is that right?
Redder. It's a comparative, like they're redder, yeah.
And now, can you go over the problems with the Big Bang theory, like some of the observations that we see that do not match the Big Bang theory?
Sure. So the biggest problem is that there are stars that are older than the Big Bang, and it's a kind of a big contradiction. There are also mature galaxies that are far away. According to the Big Bang, what we see in the distant universe is they think the distant universe is the early universe, but that's not what we see. What we see is old, mature galaxies far away, which contradicts the idea that stuff that's far away should be young, when in fact it's everything. It's young and old and whatever, there's a distribution. So that contradicts the idea that there was some expansion, and then it contradicts the idea that the far universe is the young universe. It's not the case. There are a few other problems, which are very large structures that just wouldn't have had time to form within 13.8 billion years. And there are other just logical absurdities that are required by the Big Bang, including the notion of inflation, where space expanded, and that space expanded faster than the speed of light, which is apparently what one has to believe to work in cosmology these days, and that's disturbing. And
sorry, so that's a contradiction because nothing could move faster than the speed of the light, right? That's
right.
One of the
right. And then, but I should probably acknowledge, the way they twist it so that it doesn't happen again, which is that they create a new extension and say, oh, space can follow its own rules that doesn't have to apply to what we said previously, and you must accept this. And that's not science. That is, that's people who are not honest with themselves and trying to come to a conclusion when it's not yet really a conclusion, when there's nothing backing it up. So those are some of the problems with the Big Bang. And, as I went about this, I was, trying to think about, is this really the case? Like, could could everything be like this wrong? And then that was actually kind of confirmed when I read Hubble's own works. So Hubble had there's a great passage, which I think if you Google Hubble and it's hosted on a Caltech website, where he explicitly says that the attribution of the redshift to the Doppler effect leads to a disturbing and dubious universe. Yet every modern textbook says that Hubble proved the universe is expanding, which is completely false. So how could the history of science be so wrong too? And then you have to keep the hardest part of this whole thing is checking whether I'm in some weird corner of the internet or whether this is actually real. And it turns out what I'm observing is a real problem. So then the next step was to look at redshift data. So I got all the redshift data that we have from the NASA Extragalactic database, and I did, a few sanity checks on the data, and then just plotted all of it. Just plotted all the objects, their distance, and then their energy loss. And what I found was data that could not be explained by galactic recession. And I also found data that could be explained by photon hubbling, which is light continuously decaying by a function that's e to the minus ht. So the energy that's observed over the energy that was emitted is e to the minus ht. Which actually is quite beautiful, if you think about it. It's, the photon, no matter what energy it starts at, just continuously decays from there. And the fact that rate, big H, is derivable from extremes of the atomic properties, the extreme proton charge and gravity ratios. So I suspect that what this equation will do is open up a lot of avenues for research in subatomic physics, and so that was a big realization. The next step was to look at a few other anomalies in physics, and one was the rotation curves of galaxies. That apparently galaxies rotate a little bit faster than you'd expect just from all the mass from the stars and the gas and the stars and the gas. And I think those are the only two quantities that are massive. And then I came across Milgram's model of modified
I think
dynamics.
That's the image. I'm not sure if that's the image that you're talking about. But go ahead.
Yeah, so the rotation velocity is a bit higher than a simple, force equals g times mass over r squared would predict. And then I came across what Milgram's model of modified gravity, in which he noticed that the velocity goes as was it the acceleration? The force goes as, it was the acceleration goes as not 1 over r squared, but as 1 over r. So he tested out an idea, which is, what if we take the existing simple, gm m over r squared, and then take a square root, so it becomes 1 over r, and then let's put a constant in there and see what fits. And it turns out it fit. So, and what's more is that constant that was, the fitting constant after you take the square root, turned out to be the speed of light times Hubble's constant over 2 pi. And that was incredible to me. That was amazing that Hubble's constant shows up yet again in another huge cosmic phenomenon. And a lot of work has been done on that subject. There are a few researchers, I could name a few so people can look them up. Names include McGaw, McCullough, and Lely, and they are working on just building the model to be more robust and getting more data on galactic rotation curves. They have a really nice data set of, I think, some 200 galaxies, and their function that models gravity beautifully fits all those rotation curves, even the kinks in the rotation curves. And that's something that gave me a lot of confidence in the accuracy of the model. It only requires this acceleration constant, c times Hubble's constant, and a very simple interpolation function so that it works, so that the model is able to describe gravity at solar system scales, Earth scales, and galactic scales, and that it models the kinks in the curves. Whereas dark matter, which is, the cold dark matter folks, what they do is that to account for the rotation curves, they invent invisible matter that doesn't interact with anything, and it's like in a giant blob around the galaxy. And then what they do is they massage that cloud in order to get the rotation curve that they want. And this is apparently flying in academia and getting funded. This is outrageous. Like that's not that's not science. That's it's worse than lunacy. It's like really bad. So the fact that Hubble's constant appeared in modified gravity gave me additional confidence that it's a constant. Just like Planck's constant is a constant that relates things that we see at very small scales, Hubble's constant, I think, is a constant that describes stuff at very large scales. So I think that the Big Bang LCDM model is completely false. I mean, the Big Bang never happened. Cold dark matter is not a real thing. And the redshift can be accounted for by photon continuous decay, and galactic rotation can be accounted for by this acceleration term, c times Hubble's constant over 2 pi. And I'll go a step further, which is I was thinking about where that constant comes from. And so I tried to pretend a dimension lower, as if what if all the galaxies are on the surface of a sphere, like polka dots on the surface of a sphere, and they're spinning. So what is holding that spherical set of galaxies together? It's themselves. And there's a net pull to the center of the sphere. And that pull could be modeled as a photon going in a gigantic circle. And that acceleration could be at the speed of light squared over the Hubble radius. So to rewrite, I thought I could rewrite c times Hubble's constant as c squared over c over h. So that's kind of rotational acceleration, v squared over r. And so that v is the c, and that r is the Hubble radius. So it's like a photon going in a gigantic circle, and that's that acceleration constant that's in modified gravity. So what could be pulling a photon? What could be pulling a photon as it's going at the speed of light? I thought it could be the rest of the mass of the universe. So perhaps the reason for that acceleration constant and the blending of those quantities is the dark matter, the so-called dark matter, is actually the rest of the mass of the universe. that's what's pulling the galaxy inward and speeding it up.
Yeah, that makes sense. That makes more intuitive sense than having dark matter and, like having the Hubble constant be a constant, and like your model makes more sense than the traditional model, and that's why I wanted to talk to you. For the model of the photon losing energy, I think it's Zurich. What's his name? Or sorry, the Mont model. There is a problem with it, right? There is the problem with the cosmic microwave background that apparently it doesn't match the cosmic microwave background. Have you thought about the cosmic microwave background and how that relates to your model of photon hubbling? How can we observe, the cosmic microwave background?
Yeah, I think that they are reflections of each other. So the cosmic equilibrium temperature of 2.7 Kelvin is the equilibrium, thermalization of all the starlight that's been hubbled. So that's why we have that stabilizing temperature. It's, after stars, beam out light and they get redshifted, it's like an equilibrium of like that is the temperature of the universe at which, particles can exist. And then I found, it's not yet, I'm less sure about this than what I am sure about already, but I found a way to describe 2.7 Kelvin as the temperature that corresponds to the energy density that corresponds to the gravitational binding energy of the electron in its own volume with a 1/3 constant. So that's why I'm not sure about it. But basically, if you take the energy of the electron in its own volume, that density, the energy over the energy over its volume times 1/3, that is equivalent to something being at 2.7 Kelvin. So that's why I think that it's like this perfect temperature such that electrons can exist. And there's a lot of great work done by steady state and tired light cosmologists on this. And they've been working, for the past 100 years on this, but they haven't received any funding from academia because they were railroaded out of it. So the work is there. It just really hasn't been able to emerge. And this could have been easily called, steady state 2.0 or something, new steady state or any modification of that. But I think it's time for something more sensational and something that something more sensational than the Big Bang. And that's why I call this the Big Circus. One other reason for that is that the etymology of the word circus is the word circle, which has the same roots as the word universe. And I think it's a word that can open up new thinking.
So going back a little bit on the cosmic background, microwave background. So from my understanding, when we look with telescopes outside the universe, we see this microwave background, this noise, and it's basically similar no matter where you look at, and the temperature and that noise matches a certain temperature profile. Is that right, or am I explaining it incorrectly? So based on your theory, what you're saying is that, when we look far away from here, we can just only see 13.8 billion years from here because photons lose energy when they travel. But what is this microwave background? What is this noise? Do you have a theory for that, or?
Yeah, I think it's coming from faded starlight. So it's not. It's just the temperature of this whole cosmic soup, and that's where that temperature profile comes from.
Interesting. And if that's the case, the modified gravity could make sense, because I think one of the big problems with the modified gravity model is accounting for the cosmic microwave background. And it doesn't match necessarily with dark matter, right? Like dark matter matches exactly with, the Big Bang theory and things like that. So your model would make more sense with the modified gravity model. Is that right, or am I missing something here?
I think the 2.7 Kelvin peak of the black body spectrum radiation is coming from the Hubble light. And I don't. Does it have an effect? Is that where does that account for the galactic rotation? I don't know. I think it's just the mass of the other galaxies. Maybe that mass has a total mass, but I think it's really just the mass of the other galaxies. On that though, because there is some concern on that. I think that what the cosmic, a background microwave map is actually, I think it's more proof of the steady state model than anything else. Because if you look at the history of the proposals of the cosmic microwave background, which is available on Wikipedia and the history on the history subtab of that page, the steady state theorists proposed an equilibrium temperature long before the experiments and even the theories of the Big Bang cosmologists. So 50 years before Penzias and Wilson's experiment, the famous experiment where they, the bird droppings on the, antenna or something that became a trope. Way before that, steady state theorists proposed a temperature of 3 Kelvin. So they deduced something like that way earlier, and it's consistent with a universe that is eternal and just eternally evolving.
Interesting. So one of the things that you talk a lot about, or you talk a little bit about, is that the Big Bang theory might not be correct, and the 13.8 billion years is not a constant. It's a constant. It's not the age of the universe, right? Could it be that the universe has an age and we don't know, and the constant is still the energy that the light traverses? Why does your theory implies that the universe is doesn't have an age, or it doesn't make a difference?
Oh, this is interesting. There's just an earlier start date, you're saying?
Yeah, there might be an earlier start date, or that could be true, right?
I think I'm inclined not to think that's the case, because I think conservation of energy is always true. So, you go back in time and then you ask, is conservation of energy still true? I say yes. So just, we can keep going back. So I think it goes infinitely back.
Interesting. So
galaxies keep swirling. A galaxy dies and new one forms, and those materials get recycled.
Interesting. But that doesn't affect your theory at all, right? If the universe has an age or if it doesn't have an age, that doesn't affect your theory at all, right? In any way, or yeah.
I think it affects conservation of energy, because if there is some start date, then the question is, are you violating conservation of energy? And it's like, no, there's stuff, that stuff came from something. So I think that it is, I think the right thing to say is there's no evidence for a beginning. That it's always there, it's eternal.
Makes sense. Well, going back a little bit about going back to your formula, you're basically matching, from my understanding, the photon on the proton charge radius with the radius of a proton mass black hole, with the photon. Does that imply that there is some similarity or some relation between protons and photons, or am I reading too much there?
Right. The equation is an extreme of photons. A ratio of photon extremes equals a ratio of proton extremes. Exactly. So I think there is some meaning to it. I think it makes me think that the electron is a coiled up photon, and that the proton is simply that quantity of charge and mass that is, for some reason, stable and abundant. And there are things, of course, like quarks and pions and so forth, but they're not as stable, and they just seem to be different quantities of charge and mass. So I think that there's now's a good time for people to start thinking about a periodic, like there's the periodic table of elements, a periodic table of particles, but I hope that becomes a periodic circle of particles. And I hope that the elements become a periodic circle of elements with hydrogen at the center and the rest spiraling out. A few people have done this, and I think it's way more intuitive because the table is just an artifact of row by row printing. Whereas I think that, the reason it's called the periodic, what it is that it's periodic. It rotates and it expands. So I think that's the meaning of the photon and the proton. So I really do think that the electron is a coiled up photon.
What does that mean? Can you go into a little bit?
So something happens when, an electron and a positron collide and generate two photons, right? So there's something right at that moment where something unravels. And it's up to somebody to make a visualization of that.
Interesting. Very interesting. I think we cover everything. I'm not sure if there is I have a few other questions. So have you thought about other phenomena that could be observed let's assume that photons, there's photon hubbling, so photons lose energy. What could be observed from that? Let's assume that theory is right? What phenomena and things like that?
I think if we find more galaxies, more of them will fit the trend line of energy decay as e to the minus x or e to the minus ht. The reason that number comes up is from redshift itself. So I think as we find more galaxies, more of the observed redshift will fit with this. And I think there's a big media topic called the Hubble tension, where two groups of scientists are calculating that Hubble constant in two different ways, and they are converging. And I think they will converge to the number that is the result of that equation, the big coincidence. So that's something that's to be looked for in the next couple of months, because what they're doing, the teams that are working on the so-called Hubble tension are getting better and better measurements of the constant. So I do make a prediction, which is I think that the numbers will converge on that value of h, that I think it makes that equation what it is. And if I'm wrong, then perhaps I'm wrong. So maybe it's not that specific quantity on the right-hand side. So it might not be that specific quantity on the right-hand side, but I think it still means that Hubble's constant is a constant.
Got it. Cool. I think that's it. I don't have any other questions. I don't know if you want to say anything, or you have any other things to talk about your model.
One is that I would compare the Big Bang model to the geocentric model, and that at some point we have to grow out of it and realize the heliocentric model makes much more sense, and that there are some funny transition points that might happen along the way, but we can move past those. But one, for example, that I found interesting was as they were transitioning from everything revolves around the Earth to everything revolves around the sun, that in between some people proposed that all the other planets revolve around the sun, but that whole system revolves around the Earth. So it's like, and they called it the geo-heliocentric model. And they try to compromise and be nice to everybody, but that's not. It was also false. So that's something that might happen.
Interesting. Yeah, I wanted to record and have a conversation with you because many people assume that science has ended, right?
Exactly.
We're the end of history. And that's not necessarily true, right? In 1908 or whatever, they also thought it was the end of the end of science, and there are some problems with the model that we have, the Big Bang theory, and they're screaming out loud, right? Like they're screaming, "Oh, look, there are all these problems with the model. There's the problem with galaxies being older than the age of the universe, which doesn't make any sense. Galaxies that are very distant, like they should be young, but they are old." And there are many facts like that. I actually will add that to the link of the video description. But
and if I could ask if you could link the Hubble's own words, because Hubble himself wrote that the redshift by no means is any indication of the Doppler effect of galaxies receding. So that's the fundamental problem. And it's very much like in software, where if there's a bug in the code and it's not fixed, and it's not fixed, then it gets worse. And then you have to, if you don't fix it and you want to keep the code running, you keep patching it over with stuff that doesn't ever address the problem and just makes it worse. So I consider all of cosmology like a giant GitHub repo, and we have to fix it. We have to, do a pull request and fix it.
Exactly. Yeah. And one of the points that you make, and it has been pointed out a few times before, right? That it's not like the 13.8 billion years, light years is not necessarily the end of the universe. It's a constant. And given that, you have the photon and the proton matching the extremes, like this beautiful equation, shows that it actually might be a constant. And in physics, what's interesting is that you have all these formulas that are symmetric, right? Like you have electromagnetism, and when you look at it, it's like everything is like really nice and beautiful. And when you see a formula that's really nice and beautiful, like the one that you're showing, it for me raises a flag. Oh, it might be true, right? It might be right. He might be right, and that would, like, your theory might make more sense than the universe being a certain age. But yeah, cool. Anything else?
Just that a lot of credit should go to all the cosmologists taking painstaking measurements and making the data available, and the ones who quietly worked on the steady state and tired light models, but were prevented from, their funding was cut. They were prevented from publishing, and that the most arrogant Big Bang cosmologists, like the ones who cut other people's careers short, the ones who caused the most damage, they should be fired and embarrassed and disgraced. And that really should happen. And the reason it should happen is that I think it's a source of a lot of the problems in the world.
Yeah, I agree. I agree that it's a source of problems when scientists shut down others. They should be welcoming, but it's part of their career, right? So it's very nasty, but Galileo wasn't well received, right? So, but with the internet, we have access to more information, so people can look at the data, look at the arguments, and decide by themselves instead of having aristocracy of experts, scientists, physicians that try to fit all these problems into a model that makes their career.
And it's up to, I think, a bottom-up approach to make this happen. These ideas structurally can't make their way through academic peer review. A referee actually cannot consider anything that's contradictory to the Big Bang. Otherwise, they would lose their funding. So, writing a 20-page paper and putting it through, first of all, it won't get through, and a lot of time would be lost. So I think the only way to make this work is through conversations like ours and social media, and have fun while doing it, because I think it's going to be a bottom-up scientific revolution, and it's going to free up a lot of our headspace, and I think allow people to trust their imagination again.
Yeah. Well, thank you so much, Sahil, for your time, and it's great talking to you. We'll see if your theory turns out to be right. I'm hopeful. I hope that other people come your way and challenge